بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we're going to have a new lecture, probably the last lecture about linear algebra, and one of the most important topic also. It's about singular value decomposition. Have you heard about this before? In linear algebra, no? Okay. So it's kind of a continuation of the topic that we've talked about eigenvalues and eigenvectors. It's another way on how we can decompose a matrix into three parts. It's pretty much fascinating because we're going to discover a lot of nice properties of matrices through that decomposition, and it has also applications in data science, like how you can make a recommender system. So when you go to Amazon, for example, or AliExpress, or these kind of shopping websites, they usually provide you some products that are related to your preferences. And there are different ways now. Of course, they use machine learning, but singular value decomposition of matrices is one of the ways on how we can make a prediction model about user preferences and user ratings about certain products and certain goods. So this is why we are learning this. We're going to learn a little bit the mathematical concepts to understand them, and then we're going to look on how to apply this in a data science context, like book recommendation system. So we're going to try to address these questions. What are singular values of a matrix? So we have learned about eigenvalues. Now we're going to discover singular values, and they are very much related. How to decompose matrix using singular values, and how to decompose matrix into three matrices. So every matrix in linear algebra can be decomposed into three matrices. And the product of these three matrices is going to be exactly the same outcome as the matrix itself. And how to use this decomposition in data science. So this is what I will try to address. So consider a rectangular matrix, any kind of matrix. I took just a 4 by 3 matrix. It's rectangular, it's not square, so it doesn't have eigenvalues, this matrix, as you know. And let's compute A multiplied by A transpose. So this is A, it's 4 by 3 matrix. It has 4 rows and 3 columns. And if you calculate the transpose, it will become 3 by 4 matrix. Okay, we have 3 rows and 4 columns. It's the transpose. All the rows, like this is a row, this is a column, it becomes here a row. This is the transpose of a matrix. And now we compute A multiplied by A transpose, and we find a 4 by 4 matrix. This one is 4 by 3 multiplied by 3 by 4. It will result into a square matrix. Let's move on. So it resulted into a square matrix, and this square matrix has well-defined eigenvalues and eigenvectors, as we have observed in the previous lectures. And let's calculate them. So making some computation about the eigenvalues and eigenvectors of A multiplied by A transpose, we will find 4 eigenvalues, because we have 4 by 4. So 0.98, 50.02, lambda 3 is equal to 0, and we have 40. And for every eigenvalue, we have a corresponding eigenvector. Okay, so this is a representation of the eigenvalues as a diagonal matrix. And we have also corresponding eigenvectors. For lambda 1, this is the eigenvector. For lambda 2, we have a different eigenvector. For lambda 3, and for lambda 4. And observe here, lambda 3 is 0. And this matrix, so if I take all these unit vectors, or the eigenvectors, place them one after the other, so we will have a matrix 4 by 4. Now let's do the opposite. We compute A transpose multiplied by A. So here we will have 3 by 4 multiplied by 4 by 3 matrix, it will result into a square matrix but with a slower dimension. Okay, it's a 3 by 3 matrix. And this matrix also has eigenvalues and eigenvectors. So let's do the same process and make some observations. Now calculating the eigenvalues of this matrix, we will find 0.98, 50.02, and 40. What do you observe here? The same that we have found before. So you can see, although we have changed completely the matrix, we found the same eigenvalue. It's kind of magic, right? So these eigenvalues are like a property of the original matrix A. Although they are not derived directly from A. They are derived by the calculation of A multiplied by A transpose. And of course, we will have corresponding eigenvectors. Each one corresponds to lambda I, the eigenvalues.
So,
yes?
missing lambda 0 by chance or by chance?
Which one?
The missing lambda was equal to 0. So is it by chance or that's always the case?
What is this one? Yeah, that's a good observation. Of course, when we multiply a rectangular matrix by itself in the two different ways, the dimensions, we will have always different dimensions. So the difference between the dimension, these eigenvalues will be always 0, will be neutralizing. So you will have always common number of eigenvalues which is equal to the minimum dimension. What is the difference between the two dimensions 3 and 4? 1. So here we have only one 0 value. If, for example, I take 5 by 3, I will have two 0 eigenvalues. Okay, because the minimum dimension, you will always have the same eigenvalues for both matrices. Okay? And now, organizing also the eigenvectors, we will have this matrix. Okay, this is the first eigenvector, this is the second one, and this is the third eigenvector. So let's summarize. We did the matrix multiplication A by A transpose, and A transpose multiplied by A. We observed, but we found the same eigenvalues, and it resulted into two square matrices with different dimensions. Okay, how this is useful now? Let's move forward. Now let's introduce the concept of singular vectors. These matrices that we have calculated here, they contain eigenvectors, and these eigenvectors, we call them singular vectors of matrix A. Okay, they are not eigenvectors of matrix A, but they are considered as singular vectors of the matrix A. And this is why we talk about singular value decomposition. So the 4 by 4 matrix, because we started by 4 by 3. So the left dimension, it is the number of rows. So we call this one a symmetric left matrix. Or this is the left matrix, it's called U. And this is the right matrix, it's called V. So here we have V1, V2, V3. These are the eigenvalues of the resulting matrix A transpose by A. And these are the eigenvectors of A multiplied by A transpose. Okay, so what are the, we introduce singular vectors, and now let me introduce singular values. So singular values are by definition the square root of the eigenvalues. If I take this matrix of eigenvalues, okay, we can calculate the singular values by calculating the square root of lambda 1. So this is the square root of 0.98. Sigma 2, which is the second singular value, it's the square root of lambda 2, which is equal to the square root of 50.02, this value. And here we have the square root of 40. So this gives us a diagonal matrix of singular values, which we denote as sigma. These are just definitions. Okay? So sigma will be, what is this value?
The first eigenvector.
This is the square root of 50. Now, when we create the diagonal matrix of singular value, we will organize them by the highest eigenvalue, as we did before, okay, in PCA. So this is the highest component. It's the square root of 50. This is the square root of 40. This is the square root of 0.98. And since we organized these eigenvalues or singular value by the decreasing order, we need to also to rearrange the eigenvectors to be in the same order. شفت الآن eigenvectors هذا it was like this, and now we reorganized it. So this eigenvector corresponds to this, or this singular vector corresponds to this singular value. Okay, then the second one corresponds to the second one, and so on. So we organize them into the same order as the eigenvalues. We do the same thing. So now we have a matrix U, a matrix V, and a matrix sigma. And now the magical equation is that every matrix A can be decomposed into the product of U multiplied by sigma multiplied by V transpose. You believe it or not, but this is a fact. Every matrix can be decomposed into a singular value decomposition. And we follow the same approach. We multiply A by A transpose by A. We extract the eigenvalues and the eigenvectors. We reorganize them. We extract the singular vectors by making the square root of the eigenvectors. And finally, you have a decomposition of every matrix. Does it make sense?
Yes.
Okay. So this is the concept of singular value decomposition, and it has a very interesting application. It's like now we are making the projection of A over U and then over sigma. You know, this is a diagonal matrix, so it will just scale up and down the original vectors. Okay, and the transformation, we already see that a rotation or a transformation in space is captured by a dot product between two matrices. Yes?
How do you know which matrix is U and which matrix is V?
Which matrix is what?
U and V.
Yes. The U, you know, here we have 4 by 3. So this dimension is related to U, and this dimension is related to V. Okay? Yes, the number of rows is related to U, and the number of columns, the number of rows is related to U, and the number of columns is related to V. This is how we do it. Another question?
The U is resorted after we sort.
Yes, of course. The eigenvalues or the singular vectors must be in the same order as the singular values. Okay. So now we have 4 by 4 multiplied by 4 by 3. We're going to have 4 by 3 and then multiplied by 3 by 3. You will have the same dimension and the same values as the original matrix. Okay, so these are some interpretations, mathematical interpretations of the singular value decomposition. And the properties of singular value, they are non-negative real numbers. They are always non-negative, the singular value, because we are going to make the square root of the eigenvalue. So the eigenvalues will be also non-negative. And they provide a measure of the magnitude of importance of the corresponding singular vectors in a matrix. So now we understand the concept, but how it can be useful in data science. There are many applications. And one of the applications is also the data compression. Imagine that you have a full high-resolution image and you want to store it on the hard drive. It's going to take a lot of space, especially you would like to store a lot of images of high quality. So one of the ways to compress the image, so an image is what? It's a matrix. It's to make a singular value decomposition of that matrix, and considering the property of U and V, which are orthogonal matrix, we will be able to compress the amount of data that will be stored on the hard drive. That's just for information, but of course, it's not our main scope for today. But I'm going to show you one of the applications in data science as a book recommendation system. So imagine that you have a data set like from Amazon about user satisfaction of buying books. Imagine that you have a large number of books. So in big stores, you will have maybe hundreds of thousands of books and hundreds of thousands of users. And you will make a huge matrix capturing the rating of every user to each book. Okay, so it's going to be a very huge matrix. So what will be the characteristic of this matrix? Usually, how many books each user will provide rating? So, small number of books. Imagine that they have 100,000 of books. Maybe as a user, will make 5 maximum or 10 maximum. Still, we will have a lot of zeros. So this is the concept of sparse matrix. Okay, sparsity of the matrix. It means it contains a lot of zeros. So this user has rated this book 1, 2, 3, 4, 5. This user has rated only 2 books, and all other values are zeros. So one of the ways is to save this kind of data with the limited amount of information. But in our case, we're going to use it to develop a prediction system. If I have a certain user, what will be its rating for a particular book? It's like making a prediction. Okay, so let's start from this matrix. It's a 10 by 10, and this is how it is represented. Okay, so the majority of the matrix entries are zeros, indicating that most of the books have not been rated by most of the users. And imagine I would like to estimate what will be the rating of these books by this user. I want to fill in these zeros with some kind of an estimation. So we can use singular value decomposition. And here there is a very nice interpretation of the matrix U and V. When I introduce U and V, it's like the set of eigenvectors that we extracted from the two matrices, the two square matrices that we observed. But what does this represent, the eigenvectors? So the first eigenvector, it represents like the projection of the data over the user space or the user vectors. So this U, in our case, it will capture the preferences of the user. مثلا, this user selected these books. Maybe these books are related to literature. So there can be like a hidden preferences of the user that we don't understand. Okay, some users may like literature books, some other would like, for example, scientific books, some other science fiction books. And using singular value decomposition, we can actually decompose the big matrix into U, where U is going to capture some hidden preferences of the user, and V will describe the characteristics of the books. Let's say some books are literature, some books are science, some books are computer engineering, okay? And these characteristics are not explicit. We didn't say these books have these characteristics. They are hidden. And the objective is to discover these hidden preferences and make projection into these spaces. So we have a space for the user, which is defined by its eigenvectors, and a space for the book, which is also defined by its eigenvectors if we think geometry-wise. Okay, so it's going to be like the projection of the matrix on the U space and on the V space. And this is what we define as the hidden characteristics of each. It's like the coordinate of this data set into the user space and into the book feature space. Okay, so we decompose, we will decompose A into this format, and the objective is to uncover the underlying patterns in the user ratings and improve the accuracy of book recommendation to other users. So The formal definition of underlying patterns or hidden preferences is called latent features. This is a technical word that we use in AI and data science. Latent, it's like a representation of the data that we cannot understand. It's like a feature, okay? The latent features of the data set. نفس الشيء مثلا بالنسبة للكمبيوتر vision, we start by an image that you can observe, that you can understand, a cat image for example, and then we can manipulate this picture through a neural network. It will provide us a feature map. It's a set of colors, but these colors will capture some of the characteristics of the image that allows you to make classification or detection or any kind of operation on that picture. So let's make a simple numerical application to this recommendation book. Imagine that we have a 5x5 data set of user to book preferences or ratings. We will decompose this picture, this matrix into U, sigma, and V. Okay, by applying the same rules with singular value decomposition, we will find that A is equal to U multiplied by sigma multiplied by V transpose, and this is U. Does this number make any sense? This is like the projection of this matrix into the user preference space. So these are coordinates into a different space. They represent some kind of hidden features, hidden characteristics. Same thing. This is like the projection of the data set into the book feature or characteristic space. And these are what? What are these? These are the singular values, which are the square root of the eigenvectors, and they represent the magnitude of what is the importance of this eigenvector and this one. Okay, so now, why we use singular value decomposition? Now, this is a 5x5 matrix, but imagine that you have, I don't know, 10,000 or 100,000 by 100,000 data set. It's going to be huge. So instead of considering all these singular values, we can select the top k, like we did with PCA. For example, I can say, I will select this value and this value and this value, or only these two values. Okay? So this is what we call, we will truncate the SVD matrix. We will truncate it. Instead of considering the full sigma, the full singular value matrix, I will consider the top k, these two values. And same thing, I will consider only the two singular vectors for U and the two singular vectors for V. Okay, so in this case, we will have simpler matrices. Of course, we will lose a little bit of accuracy, but still we can do faster computation that will approximate the real case. So this is a numerical application on how we can develop this one. So we will calculate the approximate A of this in this example. Okay, so this is the approximation, the approximated reconstructed matrix based on the selection of the most two important singular values. And then we can apply this to our data set. Look, now I want to estimate these three ratings for the user. And it turns out that this reconstructed matrix, it provides an estimate for the user rating. So I can replace this 0 by 1.95 as an estimated user rating for this book. And I can replace this 0 by 1.29 as an approximated user rating for, so it's a prediction model. Of course, there should be some error, okay? And as a matter of fact, these values are not exact to the exact values of here, but we will represent this as an approximation. Of course, we have only considered two singular values among the 5. This is why we will have a little bit less accuracy. So that is the end of the lecture today.